Hello, and welcome to 5-Minute Math. Today we are looking at the geometric concept of line segments, specifically how we can use the distance formula to verify congruence, and we'll do it in 5 minutes or less. So we have the distance formula here on the screen. We've got two line segments that are parallel, and they're horizontal. So we can verify that they're congruent just by counting units. So if I want to look at line QR, I can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 units. And then if I wanted to look at line ST, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 units. I could verify that these are congruent just by counting, but you can only do that if they are horizontal or vertical. But let's use this just to verify that our distance formula works, because really it's a derivation of the Pythagorean theorem, right? We're using the Pythagorean theorem here. So let's start with QR. So I'm going to say distance of QR, and that's going to equal the square root of, all right, so we need x sub 1 minus x sub 2. So let's make this x sub 1. Let's make that x sub 2. So it's actually x sub 2 minus x sub 1. So it's negative 7. And then that's going to be minus 6 squared plus, and then the y's. Just have to make sure we match up our y1s and our x1s and our y2s with our x2s. So that's going to be 6 minus 6 squared. All right, so then that ends up being square root of negative 13 squared. And that's going to be plus 0 squared, which that doesn't make that doesn't make uh, any stretch of an imagination there because it's the same y value, 6 minus 6. So really it's the square root of 13 squared, which is those two cancel out, it's 13. Exactly what we just calculated. Let's see if it's the same thing for our ST. So we're going to do our distance of ST. We need to do the same thing. Let's make this also x sub 1, y sub 1, x sub 2, and then y sub 2. All right, so our x sub 2 is going to be negative 5 minus 8. And if you're looking at that, that's going to be 13, right? And really, this previously was negative 13 squared, but we could just take the positive value of that, right? And then we're going to do plus, and now it's going to be 2 minus 2, just like the 6 minus 6. The y value doesn't change, so that ends up being 0, right? So that ends up being negative 13 squared plus 0 squared. We could just take the positive version of that, and that's going to end up being 13 squared, right? And that equals 13. All right, so the distance formula works. Now let's use it with one that's a little bit more difficult. So now I've got two lines, A, B, and CD, and they're diagonal. And so they kind of look like they're congruent, but let's use the distance formula to verify. So let's first start looking for the distance of AB. We've already got our x sub 2's and our y sub 2's and all of that already labeled. So our x's is going to be, let's see, we've got a 2 minus negative 9, all of that squared, plus our y's, 6 minus 1 squared. So what does that simplify to? Well, that's a 2 plus 9. So that's 11 squared plus 5 squared. So that's 121 and 25. So we're going to call that square root of 146. I'm not going to necessarily try to simplify that because if my distance for CD is also square root of 146, then I know they're congruent. Doesn't matter what if I can simplify that anyway. So my CDs, line CD is going to be my x sub 2, that's 7, minus, and then I've got a negative 4. And hopefully you're seeing, look at that, that's going to end up being 11. And then I've got in my y's, negative 4 minus 1. Oh, look at that. That's going to be 5. So that's going to be 11 squared plus, this is a negative 5 squared. But that's fine. That's going to end up being 121, still my 25. That's going to be my 146. So I don't necessarily need to simplify that to see. So these are congruent. And so we can say AB is congruent to CD using the distance formula.